Good afternoon. Howdy. Howdy.
Okay. Howdy. All right, very good. Much better. Everybody's awake from their carbohydrate stupor. Everybody get enough? I think there are some cookies too, in case when you go back to work. Well, we're very glad you're here. I'm Robert Wunderlich. I'm with the Center for Transportation Safety here at TTI. One of the other hats I have is we have a University Transportation Center called the Atlas Center. It's in cooperation in partnership with the University of Michigan Transportation Research Institute, or UMTRI. As part of that program, we sponsor distinguished professionals to go to the other institution and give a lecture and meet with people and talk about possibilities. And we're very pleased today to have a very good friend and a distinguished transportation researcher, Dr. Carol Flannagan. She is the co-director of the Center for the Management of Information for Safe and Sustainable Transportation, or CMIST, which is a mouthful, but what it is a lot of really great safety data. And that's part of what she's going to talk about. And I don't know if you know anyone else with a PhD in mathematical psychology, but Carol's the only person that I didn't know, but I'm sure that it helps her in a relationship with me to be a mathematical psychologist.
How does that make you feel?
Very precisely off balance. But she is a data and statistics person of great renown. She's got a lot of experience with naturalistic driving. They've done a lot of work at UMTRI with that. With crash data, particularly how it relates to vehicle safety, vehicle features, vehicle safety features, assessing the effectiveness of different treatments and seatbelt use, and a lot of vehicle-related things, as our colleagues at UMTRI often do research. She's also very well renowned for linking data together, different data sets, and she's been a tremendous help to me in understanding the linkages between, or the possibilities of linking crash and medical data. And of course, we have an initiative now here at TTI to do just that. She's a passionate believer in open data. I think you'll probably get that sometime. I have never yet had a conversation with Carol where I didn't gain some insight or learn something or think of something new that I could do, and I hope that will be the case for you today. So let's please give a warm Aggieland welcome to Carol Flannagan.
I feel like that's an awful lot to live up to. So I have to tell you, did I tell you the jury duty story? I got out of jury duty one time because they asked me what I did, and I was a grad student. I said, and they said, in what? And I said, mathematical psychology, and the judge, this is like, usually the lawyers are doing this, and the judge actually turns and goes, oh, wait, what is that? And I said, well, it's the application of mathematical models to human behavior. And he goes, I just love this job because I learn something new every day. And the lawyer said, I'd like to dismiss for, yeah, too weird for me is kind of what I got from that. But anyway, so I'm going to talk about big data, just kind of a buzzword, and so you may have had high expectations, and we'll see how it all goes. But and transportation research at University of Michigan, and obviously specifically at UMTRI. Shan Bao was here not too long ago, and so I'm going to kind of assume that most of you are familiar that she prepped you on what UMTRI is, and so I'm not going to go heavily into that, but what I want to give you a flavor for is what does the data center do, what data do we work with, and then just a couple of projects that I have been working on and sort of in safety. So we obviously are very oriented towards vehicle and occupant at UMTRI, and you guys are strongly sort of in roadway, and our worlds are coming together in the way that, particularly with connected vehicle and automated vehicle, and so that's part of what this partnership and this relationship is about, but what I'll talk about will tend to have a kind of a vehicle occupant flavor. So here's my favorite big data graphic. So I was first asked to speak on big data, and by the way, I just discovered yesterday, to my kind of shock and dismay, that if you go on the UMTRI website, there will be a thing that says a bunch of areas, and if you click on the one that says big data, there will be a video of me. And so that was, which I failed to go preview ahead of time. I was like, okay, well, it's not the worst thing, the most embarrassing thing in my whole life. So anyway, you can take a look at that and see what I have to say on that and look at the sort of stuff. So I was asked to talk about big data a couple years ago, and I was like, I don't know anything about big data. So I actually had to go look it up. And I went to the resource that we all go to first, including from the time you can read nowadays until, the end of time. The first place you will go is Wikipedia. And I looked up big data because I thought, well, I got to talk about it. I just got to find out what it is. And so this was what I found, which was actually kind of shockingly helpful. So in this, the Wikipedia version of this basically says big data is the term for a collection of data sets so large and complex that it becomes difficult to process using what you have on hand. So what's interesting about that is it means it's relative. So, if I'm a spreadsheet user, if I use Excel, big data for me, well, back in the day was more than 62,375 rows. Now they've expanded that. But in other words, it's data that's kind of ahead of the tools that we have to work with. And so that kind of idea of big data being relative is something that I'm going to eventually loop around to the end of this talk and kind of think about whether that is all there is to big data. Is it just always just bigger than what we can handle right at the moment, or is there more to it? And hopefully I'll convince Bob you can take away whatever you want from this, but I have some thoughts that it's not quite that simple. But anyway, so quick slide on OMSI. And feel free to ask questions, although the last time I said that, then I got so many questions that then I didn't get to the end of my talk, so, but, I talk very fast, try to not do that. Anyway, what are the odds? I gave a talk at one time in European, there was this, I was giving a talk to this group that was a Euro FOT was this big European field operational test, and I was talking about data analysis for field operational tests. And at the end of it, the one comment was, wow, I've never heard anyone speak English so fast. And I was like, and of course, only 2 people in that audience had English as their native language. And then I just felt really bad. That wasn't, my material was great. But anyway, so OMTRI, sorry, but I digress. OMTRI has a somewhat over 100, so we're quite a bit smaller than you guys. We've got a little over 100 faculty and staff. We've got 25 faculty when I wrote this. We've actually been hiring, and I think we're up to 29 at this point, which is really exciting. It's really nice because we're growing, and they're young, and they're full of vigor and ideas. It's great. And so we have about a $25 million a year research program. This, the 80% government is by the dollar amount. If you counted projects, I think industry projects would be a larger percentage of the total number, but we get these handful of large-scale, single kind of government projects, and I'm going to assume that you've heard of some of them, although I will talk about them specifically, but stuff like Safety Pilot, which is a connected vehicle project. So that's OMTRI, and again, I'm happy to talk to anybody about in more detail, either while I'm here today or in the future. You're always welcome to email me and get more. So back to big data. What good is big data to a research organization? And we'll say my angle on big data is all about being part of a research organization. There are other, companies are mining big data. There's a lot of talk about unstructured data, mining Twitter and all these kinds of things. We don't do that. We have structured data, and we're dealing with research questions. But so that's kind of my take on it. So first off, large samples. We're dealing in a world of rare events. Crashes are phenomenally rare events. As much as every one of us knows somebody who lost a relative or something in a crash, they're phenomenally rare. And so when in the world of data collection and the amount of time people have to drive around with your vehicles to get into any kind of trouble actually makes it kind of hard to look at any reasonable collection of crashes outside of a crash data set, let's say. So many observations, large samples are needed to actually get at the kind of safety issues that we're interested in. Taking many different measurements is useful. And a lot of the time, this sounds really terrible, but a lot of time we collect data, we don't actually know what we're looking for at the beginning. And one could argue that that is a poorly designed study. One could also argue that it's an efficient way to get data for future use. And in these cases where we're doing very expensive, very large-scale data collection in field operational tasks. You know, if you stick another accelerometer with the angular momentum thing, it's not that expensive, but boy, it's great to have when you get to the end. So video is video is all about that. They're going to do some stuff, and we can't detect it with our sensors, and we just want to know, you know, we're going to look at the end of it. It's got this kind of interesting quality for data analysis, makes it hard. Greater density of data is it helps us build better models. So back in the day, sampling rates might have been 1 per second. We're now sampling at 10 times a second for most of our signals, which is kind of below any rate of reasonable change. So we can get very detailed information about speeds and accelerations and all kinds of things. And similarly, if you improve the quality of video, you can actually see more stuff in the video. It also takes up a lot more space. So that makes it big. It's just more bits. So one of the other things I did when I started accidentally becoming the face of big data at Umtree, which is kind of crazy, but I started going to talks because I thought, again, you know, I should probably know something about this. And so I went to this one in statistics that was given by a woman named Bin Yu, who's at Berkeley, and she's actually computer science and statistics, which turns out to be kind of an interesting field to be in. And she described what she thought were she describes the 3 dimensions of the big data enterprise. And I kind of like her way of structuring this, and so I've stolen it. I'm trying to give credit. But so basically, she talks about humans, data, and computation, and I'm going to kind of structure this along those lines. So data, what do we have? So CMIST, as Robert's pointed out, CMIST is great if you just use the acronym. And if you try to say out the words, it's a unreasonable mouthful, but that's, you know, you don't know these things when you make up your acronyms, you know? You make up an acronym and you're sitting there and you think, oh, good, and then you don't, and then you can't change it. So we were kind of launched in 2012, and actually we grew out of the Transportation Data Center, which had been at Umtree more or less from the beginning. We're about to hit our 50th anniversary this summer, and you can all come up for the party. But anyway, so the Transportation Data Center was exclusively focused on crash data, and so we have so much more going on at Umtree now. So CMIST is kind of our entry point to data at Umtree. We are not the only ones with data. Everybody in the building works with data. It's kind of necessary to do our jobs. But we can tell you who's got what, and some of it we make available, and some of it we house and curate, and some of it is you know, my colleagues are housing it, but I can tell you what they do, and in fact I'll talk about some of those things. We have our CMIST triangle, and this is kind of what we do. We do 3 things. We actually do a lot of things, but they fall in these 3 categories. And one of the important things about the CMIST triangle is that transportation data analysis to answer questions and save lives is at the top. It's the thing that that's what we do. But it's supported by these 2 other activities that we spend a lot of time on. The data dissemination, and Robert sort of alluded to this, and I've got slides coming up, is all about getting data out there. We cannot make progress in research with these kinds of data, and big data is actually is sort of more extreme than a lot of things. We can't make progress unless we get stuff out there and give other people a chance to work with it. I only have so many hours a day. It doesn't help me to keep it close. The other thing we do a lot of, and I'm actually just kind of a math geek, and I'm a stats geek. I love methods development. That's my favorite activity in the day. But it has to kind of be moving towards answers to questions. So we do a lot of that too. We work on methods development for naturalistic driving data and methods development for other stuff. So data that we have, as I mentioned, we have this long history of housing crash data. So I have a staff member who's really good at this. She just, because I'm really bad at this sort of thing, she cold calls states and says, hey, can I have your data? And then she develops relationships with these people, and they just send us their data. So we've got repositories, and and this says 5 to 10 years. We have data from states going back, decades. And the irony is that as old data, especially crashes and driving, actually isn't considered of super cool historical significance. It does just kind of age, but we have it. It's still sitting there. Some of it on, I don't know what, the old, little discs that had the little spinny thingy, and you stuck them in the thing. I think they were called Flaggabits. So we also work extensively with the national samples of crash data sets, which are really good samples that can be weighted up to national statistics. They have kind of special analysis with them. But we do a lot of work with those, and we try to make them a little bit easier to work with. Those are free and open on the web. You can just FTP them and work with them at any time, and that's it collects that stuff. We have, and I'll show you, a lot of driving data. So I'm not sure how much Shan sort of went in, but for quite some time, for the last couple of decades, we've actually been running field operational tests for U.S. Department of Transportation. So a field operational test differs from a natural speed driving study in that we're looking at how a specific system, a safety system, works. So a long time ago, the first one was looking at adaptive cruise control, the ICC-MOT. And so we would get vehicles, and they were often prototype systems, typically prototype systems. We get vehicles from manufacturers that have these systems. We give them to subjects or drivers, and people go out and just drive their normal driving in our vehicles. And let me tell you, it's not hard to get people to participate in your study when you give them a car for 6 weeks. So I don't know how many of you are familiar with Shark 2, but people talk about the natural speed driving studies where you're working with people's own vehicles, and you're coming in saying, I've got a drill here. Could I put a camera in your car? Would that be okay? It's a lot harder to get people to do that. But they're happy with the cameras in our car, and it's fine, because we give them a car for 6 weeks. So they go out, and we generally run baseline for a couple weeks. So we turn all our systems off, they drive around, and then they come back in, and we turn the systems on, and then they drive around with those, and we sort of look at, how did their driving change? What happened when alerts went off or when other things were done? How often did they use the system? We don't allow them to turn it off, but how often did they initiate ACC and so on? So we've been doing this now for a long time, and all of these data sets have driving of various sorts in addition to driving with the systems. We're driving without the systems. So we're building up a large repository, and they just get bigger and bigger. And our DASs get small. Our data acquisition systems are these boxes. They get smaller and smaller. So the most recent one of these, our most recent couple, are the IVBSS stands for Integrated Vehicle-Based Safety Systems. And this was in response, NHTSA was concerned that with the proliferation of warning systems, that if you got yourself into a certain kind of trouble, all the warnings would go off and you'd be paralyzed or do the wrong thing or something. So that was the kind of, and this was I think a $11 or $12 million study for that, which is an important question. Turns out the answer to that question is actually the first thing that goes off, people just kind of respond to the situation. So it isn't a problem. Also, it doesn't happen very often. But the great thing was we got out of it, 108 drivers for 6 weeks apiece in vehicles that were heavily equipped with all the stuff. Radar, so we know a lot about what's going on in the environment through numeric data, which are a lot easier to work with than video, but we also have video, we can see. And so we mine these data all the time. Questions of seatbelt use and, and obviously secondary distraction and all sorts of other things where you ask, actually one of them was headlamp high beam use, turn signal use. So these questions that were never the questions of the original study, but the data are there and they're actually really pretty useful for this. So that was kind of cool. We always show videos. We always show this guy because he's really interesting. So I don't have sound, but I think, here we go. So, and I'll show you again because sometimes it's hard. There's a lot to look at, but he's texting and. 3, 4, 5, 6. Yeah, exactly. So this is an example of actually, the warning was clearly about in this situation, and that is the kind of thing they're looking for. But one of the things you can see here is that, we've got, these are just a handful of signals that we've got. There's all sorts of other stuff. There's GPS. There are all these. You can see what is feet. Actually, they don't have. You can sort of see. So there's an enormous amount of information in this data set, and enormous opportunities to answer lots of questions that were never part of the original. Safety pilot model deployment is the one that was just wrapped up recently. This is all about connected vehicle. So it's a little bit different from the other FOTs in that we're actually using people's own vehicles, and then we install most of the vehicles. We just install the transponder that sends messages out. And then in a smaller number of vehicles, we actually had cameras and data acquisition systems and warning systems. I have one of the in-between. My vehicles are actually equipped with what they call the aftermarket safety device. So it's beeping at me all the time, but there aren't cameras. So we had like different levels. We had city buses, we have school buses. So there's all sorts of stuff. These vehicles are driving around, talking to each other all the time. And part of the goal was just to get enough interaction between vehicles, because you have to see the environment with these messages. We also had a lot of, we had roadside infrastructure installation. So then you could be sure that people, every time they pass that thing, you get the curve speed warning if you're going too fast, and then the roadside, the equipment is downloading data every time a vehicle goes past. So that went for a year, and we ended up with about 1 petabyte of data, including messages and video and warnings, and we're just starting to kind of wrestle with how do we work with it. We've worked with it a little bit, and are also working to make it available. That's, you know, this is a really important data set that other people need to have access to work with. But it's pretty cool, and so that's sort of and it's much larger than the previous one. So that's driving data. We have anthropometry data. So we have our largest group, actually, which I'm also part of, is the biosciences group. And we've been concerned about occupant protection for, you know, since the beginning of OMTRI 50 years ago. So one of the challenges of protecting occupants in vehicles is they come in really different sizes. And in fact, dummies do not. Dummies come in 3 sizes plus a whole pack of kids. And I'll talk about that a little bit. But basically, measuring people's shapes and sizes really becomes important in understanding occupant protection. So it used to be that when they ran one of these studies, they would come and they would have people sit with those. You remember those things at the doctor's office, the thing and the thing? You know, you sit there and they're measuring like little parts of and writing all this stuff down. And then in the 90s, we got cooler because this is a point machine. So you point it at a body landmark, some bony landmark or something, and then hit the button, and it goes directly into the computer with a point in space, and then you can work with that. Now we have the full body laser scanner, so you stand in there and go space aliens, and then your body shape comes out. It shows up in the computer, and so we can run these studies. We can run lots of people in these studies fairly quickly nowadays. It's just not nearly as labor intensive. So through a series of studies we've built up populations. We've got populations of people's body shapes and sizes. We also have, we engage in the more time-consuming activity of having undergrads code x-rays. So we actually also have bone dimensions underneath that sort of body exterior. So we have we're kind of piecing all the parts together. And again, I will talk about this a little bit more later. But so let's see. We also have a simulator. Simulators are really interesting, and I can't even touch Sue's expertise in this. But what's interesting is that at least with ours, which is a fixed-base simulator, it's a car body, and then we've got screens in this room and some kind of cool software that's pretty easily manipulated to do lots of different things. And you can work with the interface. Simulators are used to study things that are too dangerous to do out on the road, or where you need a lot of flexibility in maybe the interface, or a lot of control over the situation you want to run people. They tend to be small studies. So a simulator study is typically answering a specific question, and with a smaller number of subjects. What kind of intrigues me, and to be honest, we haven't really. I don't know if you guys did this, and we certainly have not put in the effort, but there's a lot of information over the 100 simulator studies that have been done, and at some point, if you started to stitch that together, you would actually have a very large body of simulator data. But I think stitching it together is a little bit more challenging, maybe a metadata management system or something. But this is really more of a tool at this point, but the data are just like driving data. So the methods and the way you use it is, they're time series signals of kinematics and things like that, and so the methods that we develop apply to these data as well. Spatial data, again, everyone in this room is a greater expert in this area than I am. But we have our TOAST data of spatial data as well. We have a couple of, we have limited expertise in this area, but are kind of making use of it more and more because again, you know, the infrastructure world and the crash world and the vehicle world are not separate worlds anymore. And this is really a great, this is a great opportunity, and we're really interested in really trying to kind of develop this skill set to understand. So the simple ways that we make use of it are we pull information from spatial data sets on road characteristics. In one of the studies that I'll talk briefly about, we use GPS to give us things like solar zenith angle, how dark was it, are they staring into the sun, road functional class, and just a couple other sort of things. And we just pull that into our other data set to work with as additional predictive variables. But this is also, we're doing more kind of in this GIS world. This is what I claim to be a map of my brain. It's only a partial map, but the idea is that the blue boxes are these various sorts of data sets, and then the yellow ones are kind of the path to linkage. And the point here is that all of this stuff is ultimately, to one degree or another, linkable. And when you integrate data, you actually learn more. You have a richer information to work with. So this is an area that I do a lot of work in. And as promised, data hosting and open data. We need to put stuff out there, and it needs to be available, and it needs to be reasonably priced. Ideally free and open. You know, I don't know if you guys are familiar with Obama's open data memo, but the open data memo basically said data that are collected by the federal government with taxpayer money needs to be free and open. And then all the domain repository people, so these are like data center people. I've participated in some of these meetings of other data centers, and they're like, we're totally on board. Could we have some money? And so it's not, you know, it's not free to me to host data. So this is a real problem. This is, you know, there's no question it's a public good to have data available, to have more people, all of you working with my data, because all of you will have a million better ideas than what I have. I can't do this. So this is just this kind of ongoing, you know, piece of what I'm trying to work towards. We're interested in, you know, we have had a lot of conversations about hosting SHARP2 data, which the data were collected specifically for the purpose of making them open. There was no other goal to that study. So these are things that we struggle with the business model, and we're slowly trying to kind of build up a reasonable business model of open data, and hope to kind of promote that as I go forward.
Well,
sorry.
That's it for me.
That was brilliant timing.
Thanks.
That was really good. See you later. So,
Yes, he doesn't support it.
So he apologized to me because he had an appointment, and I said, what you need to do is you need to, at the right moment. I'm so offended I can't speak. So, sorry. That was great. Open data, you guys, come on. Don't be. Okay. It actually surprised me. He promised he'd do it. So computing, which is you know, computers. I just want the computers to work. You know, that's sort of my attitude, because I'm a tool user and I'm not a computer scientist. We're just in this perpetual battle with data set size and data structures and everything. And sometimes it really is just it's only money. Just give me more money. And then you buy bigger things and faster things. But there's also the somewhat more interesting way of dealing with this is to actually build more efficient data structures for the data we have. And as our data sets are getting bigger, the data structures that we've been relying on are not scalable. And so this is another kind of area of work that I'm pursuing largely with collaborators and people who know more than I do. In addition to that, software tools have to evolve, and we're developing. One of my kind of visions is to develop a sort of direct web-based access tool that allows people who are not experts in MATLAB and SQL to do filtering of naturalistic driving data sets. So there are a lot of people that I have these conversations with people that are like, yeah, you can't do that. And I say, well, if we can't get this out to people who are smart but not experts in SQL calls to naturalistic driving data sets, we will still only have the 10 of us working on this problem. So I keep pressing on, and you know, eventually when we get enough students through, we'll have a tool. But meanwhile, we're working on collaborations with the computer science department and trying to kind of move this forward. But we have built metadata management system for all of our crash data and some of our other data. We're working on variable standardization. You guys are familiar with states crash data sets. Every state, 50 states, 50 different schemas. It's just nuts. Except wait. When you feel like whiny and sad about that, which I do on a regular basis, you should go to Europe sometime, because they have 28 countries, 28 language, 28 schemas. It's worse, and they don't share well. So I've been humbled by the fact that I can read the code books of every state. That's a thing. But we're working on variable standardization across states. We bring these things in, we identify, we common code the engagement variables and so on. And I'm like, never going to finish this thing if I don't get it moving. So, okay, so humans. There's this great quote from the Harvard Business Review: big data needs to be complemented by big judgment. So there are a lot of computer science in particular is really excited about sending stuff out into the data sets and bringing back knowledge. And Watson is a really good example. And I think it's great. But somewhere it's good if somebody at the other end who is human is kind of making sure that things make sense. And so that's why I claim that I should still have my job. So I can oversee what Watson's doing, because surely that's a good plan. So I'm really, mostly this is what I'm going to kind of talk about. The next few things is really just research that we're doing, which is the human component. Is how do we answer questions and how do we kind of make use of these data? So data integration, I've talked about. I'm heavily involved in working on data integration at the state level, and specifically, this all arose from this NCHRP 1757 project, which is about measuring serious injuries and crashes. So MAP 21 says, now, hey, we've been doing really well in fatalities, now you're going to measure serious injuries. So the Federal Highway was then given the job of defining what that meant, but meanwhile, the TRB put out this project to say, first off, recommend a definition of serious injury, and secondly, tell us how to link data at the state level. Because really, police-reported injury, CABCO, is not random, but it's not really that great. And so if you link, then you can get this path to medical outcome data, and you can really measure serious injury in a medical outcome kind of way. So this has been really interesting, and at this point, we've created a roadmap. I've given several talks on this topic. I'm going to talk again in March at Lifesavers, and the panel is actually going to continue and expand the focus of the scope of this project. So I'm eagerly awaiting that. One of the things I really get a kick out of is sort of statistical simulation. I guess although this was both engineering and statistical simulation, but sometimes we're just missing information. We have this project where we're trying to understand the benefits of a collision mitigation braking system. So collision mitigation braking is automatic braking in response to a hazard in front. They're looking, NHTSA in particular is interested in whether heavy trucks should have this on it. Is there a benefit? Because it's really bad when heavy trucks run into cars. It's just a bad thing. And so they're trying to figure out, what would be the lives saved and so on. Well, in order to do that, we need to understand what would the system do. In order to do that, we need to know what happens before in the kind of pre-crash period. And that is actually far and away the weakest data area that we have in our little world of drivers and crashes. We have very rich data sets with normal driving, almost entirely. And we have very large data sets of crashes, and we're having a really hard time filling in the bit just before the crash. So So what we did, and truck and a car are not even in the in-depth crash data set. So what we did was, first we needed to be able to represent the CMB system. So we did some track testing because they gave us the trucks but not the algorithm. I don't know, I wasn't involved, but and then we use driving data to understand basically situations where a truck is following a car. We have truck naturalistic driving data. And then what we did was we sort of played things out to simulate, they were simulated crashes. And then once we had that, we had all the kinematics of these simulated crashes, then we could implement this all in simulation. We could implement a variety of algorithms. But the trick is that those simulated crashes are in whatever representation they are. So then what we did was we used the crash data set to restructure the simulated crash data set so that it looks like real crashes, looks like our crash data set. So I will play you, the videos are. So this is track testing. That one went well. That was mitigation. So it was going a little slower than it would have. So the simulation approach, we had real-world kinematics because we had trucks driving around following cars and being forced to brake. It's just that our drivers were doing well and they braked in time and there weren't these sort of emergency situations. So we simulated a delay in the driver's response, and then we simulated what would happen if they. So what this is just the point here is this was a braking profile for truck drivers that we implemented, and there was and we took it from examples of truck driver braking. The problem is we're talking about if you're imagining a dire situation, you need a fairly hard braking profile. So this is not normal braking, and there was actually some controversy over whether -3 meters per second squared was a reasonable braking, and we're running it again with this is when things get exciting. Then what we did was we took existing initial conditions. So this is a real car, lead vehicle car decelerating the way it does. It's kind of wacky. And then we had the truck speed of the initial conditions, the distance, and all this stuff. And then we just played it out. We said, okay, so what if the driver just wasn't looking? What if they were looking at their phone or out the window, and they delayed, 1/10 of a second or so? And so then you see, this is a sort of a somewhat confusing diagram, but basically, if you get to this axis, it's a crash. If you get back by the time above this axis, it's not a crash. So this is, I think it's a range rate diagram. So if you delay a little longer, things go bad, but then they are manageable. And then this is sort of the last one that doesn't result in a crash. You're just going to kiss the bumper. And then finally, if you delay this long, then you can't get back with that. So we just did that, and we created a whole bunch of these simulated crashes. But then the question is, but is this a reasonable population? Because if this isn't a reasonable population of crashes, we don't really learn what benefits are. We actually need a reasonable population. So we took, the blue is the distribution of what we got out of that activity. This is the delta V, or crash severity, of the crashes from that sort of simulated set. It's just kind of random what we get there. But we reweighted them so that they look like the crash distribution, and that was this sort of process. So now we actually have this kind of cool sandbox. We've got a whole bunch of these, if you buy into the methodology, we have a whole bunch of crashes with, all these simulated crashes with full information that you can actually implement any algorithm with, and you can kind of look, how does the algorithm do, and so on. So there are other people taking other paths to the problem, but it's a challenge, and we're working on repeating for light vehicles at this point. So let's see, it's 1 o'clock, right? Is the
Keep going.
time? Okay. Yeah, everybody else.
If they start walking out, then.
Okay. All right. Well, I'll go. So parametric human body modeling. Remember all those bodies? We got all those people and the laser scanner and everything. So like I said, crash dummies, which are protecting you guys in your vehicles, there are pretty much 3 of them. 3 adult crash dummies. One of them is actually, I'm pretty close to the size of the mid-sized male, so hey, lucky me. And then there's the small female who's a 5th percentile female. This is about 5 feet tall and under 100 pounds. And then there's the 95th male, which is probably about you. And that's it. They put them in, and actually one of the hilarious things is they always put the 5th female in the passenger seat. It's like, yeah, because they never got it. So we would like to do something a little bit richer for the very rich, assortment of sizes and shapes of people who may not be well represented by the crash dummies. So we do this, so we have the body scan where we scan bunches of bodies in lots of different sort of driving positions. And then what we do is we actually start building parametric models of these. So we model the size and shape, and then we can actually kind of statistically manipulate these sizes and shapes to represent a population. We can also envision the population. So we know what the population is. There are very good studies on sizes and shapes of people in the US. The National Health and Nutrition Examination Survey is where we get that information to produce population at large. But we can envision the future. We can envision an aging population. We can envision a different country and its population of people. We can do all sorts of stuff like that. So these are our parametric human body. These are now modeled. These are not any one particular person. They've been kind of morphed and altered to be related to, to sort of represent the population. And then we stick them in, here we go, in these occupant protection simulation environments. And this guy, this will just kind of repeat. This guy is a BMI of 40, so he's pretty, so watch that. What's going on there with the steering wheel versus this one. They're both belted. There's no contact. So this is a safety issue that needs to be addressed for the population as our population grows larger, although I understand that's starting to tail off. But we have an issue with obesity in this country, and they are at greater risk in crashes, and so we're trying to understand that, and we're trying to understand that through this modeling. There is no obese crash dummy. So it's my goal actually to kind of structure, and actually many of my colleagues are working on this too, is to kind of have a paradigm where we can look at the population of crashes and not just be working. Not only do we only have 3 dummies, but we have tests that are all very, very extreme conditions. And the concept is, well, if you can save a 95th percentile male in a 40-mile-an-hour crash, everybody else is fine. And that's not true. That's not. And the whole airbag debacle of the 1990s was a perfect example of that. So small women were being killed by airbags that were designed to protect large unbelted men, and it was like, well, okay, so it's more complicated. It's an optimization problem. And so this kind of simulation, we can only run so many physical tests, but optimizing, in simulation can help. So I'm getting to the end, and I'm just going to wrap it up. But basically, the question that I sort of promised to address is big data always relative? And I think it's not that simple, because what I'm sort of seeing is, particularly in transportation safety, we rely heavily on what I call handwork. So we feel very comforted by watching video, because we drive too. And you watch video of a driver, and you do things like, you have undergrads who watch people's faces and say, are they surprised? Oh my goodness, they're surprised. Or they watch out they say, is this a critical situation? Would this have scared me if I'd been driving? So there's a lot of, and that's not, I'm not arguing that that's a wrong way of doing things, but it is, we're very comforted by that. And we need to be able to get to the place where we can actually send algorithms out on big data that don't rely on that, or that are analyzing the video itself to do what our undergrads take too long to do, as wonderful as they are, or too expensive to do. So handwork, so changing from this kind of very small focused sort of thing to a system where we feel comfortable with algorithms that just look at the numeric data, and you can do it quickly, and you can work with the whole data set. That's where, to me, big data really does become kind of different from other things. So I think I'm going to skip through this. We have this cool project that's on videoless data. So we're collecting very large volumes of very targeted data with no video, without the help of video. And so we're really having to kind of learn, how do we understand what we're seeing if all we're looking at is numbers. So here's the thing. What I'm calling small analyses of big data, and I'll tell you that 99% of what I do, I would classify as small analyses of big data. So where big data is it's a lot of data, and if I have a question, I can go into my little corner and I can dig those things out and I can do something with it. And that's what I mean. That's still handwork at some level, that filtering. Big analyses of big data are where computer science has really been working and where I think statistics really needs to go, and where I'm hoping that, that we sort of, I'm developing collaborations in this area to just kind of test this idea out, is what can we get from that versus what do we get from facilitating lots of people to do these more small, these more small scale filtered analyses of our big data sets. So that's the story. And other questions?
I was really intrigued with some of the data that clearly has people's faces or human issues. What kind of handle IRB issues?
Excellent question. You notice I'm showing you this guy. So we get agreements with our subjects that are substantially less restrictive than I think anybody in this field in the world. And so we have a lot of freedom, and we don't post it on YouTube, but we have a lot of freedom to use these. They agree to it, and in fact, they have a separate checkbox that they can choose not to check. And out of 108 drivers, 104 people said, yes, you can use my video in presentations and in whatever you share. And so we share video much more readily. We do this. On the other hand, as a data center, one of the things, part of my job is to make sure that we're complying with anybody else's requirements for PII, for personally identifying information protection. And so I have, I'm working with folks in Sweden on cross-ocean video coding methods that allow them to sit in a room that is appropriately vetted with the lock on the door and the no internet, but their computer's connected to my server, and do remote access and make sure that the video streams at a high enough quality and fast enough rate that they can do video coding and vice versa. And then what we do is we have these sort of remote sites that are themselves meet a set of criteria that we've decided are, and like I said, our criteria are less restrictive than theirs, but we can make our site meet their criteria if we want to kind of code their video. And this, to me, is part of the solution to the Shark 2 problem, is that the Shark 2 problem right now is, if you want to video code Shark 2, you have two choices. One, you go to Blacksburg and do it yourself. Two, you pay them to do it for you, and that's it. And, there's no way that you can get enough people to do that. It's completely inefficient and doesn't get stuff out in a timely way. So if we can set up these kind of connected analysis centers around the country and around the world that are secure and have been site visited and have been stamped as meeting whatever the requirements are, then there's no reason why we can't do our video coding that way and still protect subject privacy. But there's just a basic, this is a problem in all kinds of fields. Actually, education has it worse than us because they're videotaping kids, and it's way more sensitive. So this is a thing that a lot of data centers are working on, and we're certainly concerned about it. But part of our end run around for our data sets is they'll participate in our studies for much less severe restrictions. So, other questions?
For as much data as you have, it's kind of one of those, catch-22. You want as much data as you can get, but when people are actually using it, what do you find is actually useful for, a size?
Right. Yeah, and that's why I'm spending so much time trying to kind of build tools that give people. So right now, there are a handful of people in the building who actually aren't me, because I haven't sort of taken the time, who are really good at extracting data. So that's a bottleneck. That's a limited resource right there. And so you go, and, usually it goes pretty fast, and you can go to them, and you can sort of get stuff from them. But there are clearly huge, chunks of these data that hardly anybody is ever looking at, and signals that hardly anybody is ever looking at, and then other parts that we're just beating to death with a hammer. But you never know, you don't know what that's going to be at the outset. So I still really think that what we need are we need cost-effective ways to store it and get access. And then the idea is to remove some of these bottlenecks by providing tools that people can get in. And if nobody ever uses a hunk of data, I mean, if you really wanted to save space, you could probably assess that at some point. No one has ever pulled this particular datum, we're going to put it in the archive or something like that. But I think it's a real issue. But right now, everybody's really kind of thinking in terms of, gosh, we just don't even know what the questions are. And so there's a strong bias towards saving it where you can get at it for now. It's a great question.
I have a question on later you mentioned about computer science kind of models there. Is that more along machine learning, artificial intelligence going to down the road?
Some of them. So the ones that I know about are Federal Highway has this exploratory advanced research program, and they are really, so the video problem, this PII problem, I was talking to Charles Fays, there are these kind of two fairly disparate paths to solving it, and they're both good. They'll both sort of help. The computer science version, which uses a lot of machine learning algorithms, is kind of just trying to do your video analysis for you. So let the computer watch the video for you, and then there's no problem, right? Because the computer's not going to tell, it's not going to put it on YouTube and everything, and then it will all come back. And of course, the downside of that is you really need to know what are the performance metrics for that algorithm. So as a statistician, I worry about, I'm actually not bothered by it being wrong some of the time. I just want to know, how is it going to be wrong? What's my 2x2 matrix? True, false, computer judgment, yes, no, real life, yes, no, or human judgment, I guess would be a better, and then how do those things line up? So, but they're very excited about the computer vision, and then the Federal Highway, the EAR stuff has gone to Carnegie Mellon, and University of Wisconsin has one, and several others to do these kinds of image processing algorithms. My angle on it is that you can, if you give people access in a protected environment, if you work on that technological solution, make it work in a way that doesn't give people an easy way to make a mistake, to let stuff out, then that's kind of an alternative. And I think those are both good paths.
But they allow them to cross-check.
Yes, exactly, yeah. So, but computer science and big data is really just, they're just going wild. It's a lot of fun and stuff, and like I said, with the unstructured data and the language data and the Watson and all that kind of thing. And I go to these talks. I'm a statistician, and I go to talks in statistics all the time. And statistics is just kind of having a fit about this, because it's not in there. It's not really very. This stuff is not easy for statistics. They really do small analyses. I mean, you can have a big data set and you can run a model on it, but your way of thinking about it is really different. And so that's why U of M staff's department hired two computer scientists to be in their department, but it's a surprising struggle to figure out how to, and computer science, they're like, algorithms, and you're like, excuse me, have you checked the bias qualities of what you're getting back? I'd really like to know. Can we measure the variance? And, they're like, yeah, whatever. My stuff is cool, and I work at Google. And so, those guys aren't cool. And so I'm just, I'm kind of reaching out to try to figure out, how we can work together. And University of Michigan has a whole program on data science and that. Other questions?
Anybody else? That's it? Too much. You gotta quit getting positive.